From theory to practice, second order energy corrections in quantum mechanics. Part A. Find the second order correction to the energies En2 for the potential in problem 7.1. Recall the problem in 7.1 dealt with the infinite square well, so that should ring a bell with a delta or a bump. And comment by the author. You can sum the series explicitly obtaining -2m parentheses alpha over pi h bar n to the square for odd n. Part B. Calculate the second order correction to the ground state energy E02 for the potential in problem 7.2. Recalling that was dealing with the harmonic oscillator. Check that your result is consistent with the exact solution. And if you recall, that exact solution looks something like a power series with the square root that we dealt with. But of course, why do we care? Well, again, not all systems are ideal like what we first studied, so this perturbation theory, especially in the higher order, is simply to get better accuracy with the systems that we're measuring. So, with that, here's the challenge. What systems require a second order correction? And I'm thinking something potentially in chemistry, not quite sure, but let's see what you think or what you find. That being said, don't forget about the PDF that can follow along, and there's definitely some stuff left out of this question. That was just too much to put in a brief video, so access that using the link below. And if you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. Alright. On to stop number 1, which is part A. So let's recall then that from problem 7.1, we know that the perturbed Hamiltonian was alpha, the magnitude of the bump, with the delta function located right in the middle of the well. If you recall, the infinite square well ran from 0 to a, so a over 2 was right in the middle. And so what we need via equation 7.15 is the expectation value of two states, the psi-m state, which is with the 0 order, so the unperturbed, and psi-n. Okay? Thankfully, since our Hamiltonian has a delta function, we can find this pretty quickly. Recalling then that from equation 2.3, we have the wave function for the infinite square well, and we can go ahead and chop this up pretty quick. Take the constants outside, you have a square root of 2a, square root of 2a, so that gives you 2a that you see here. The alpha can go on the outside, and because we're integrating a delta function, we know that we just need to evaluate the integrand at the spot of the location of the delta function. That being said, we plug in a over 2 and we get some nice cancellations with the a's from the wave function. Cool enough. And then we're left with a composite of sine with m pi over 2 and n pi over 2. Of course, as we recall from 7.1, we often got that for different combinations of numbers, meaning that one was even, one was odd, we get some characteristics of these sine and cosine, or sine and cosine, so trig functions in general. But we definitely know, based on this format, that if it's an even number, so 0, 2, 4, 6, all of the above, we know that if that's the case, sine is a factor of pi, which goes to 0 for all evens. So that's pretty nice. However, when dealing in combinations of odds, which we see in the second piecewise there, it can be either +1 or -1, and they're not always overlapping, so we have to have a plus or minus there just in case. Thankfully, though, from this modification, we can obtain En, or the second order correction, because we have absolute value squared. So that takes care of that completely, and we like that. But for the energy terms that we need to from equation 1.75, we know that we need the energy of the infinite square well, which is given by equation 2.30. So we're good to go. And as always, we have about 1,000 steps of algebra, give or take. So let's just go ahead get everything nice and factored out, we see that we could bring the 2 alpha A outside, the pi squared h bar squared over 2ma squared, that can just come out from the n state and m states. Again, noting here that we cannot have m equal to n, and it only exists for odd numbers, so odd integers. And from that, we can simplify this pretty quickly. You bring out, well, recalling then that dividing by a fraction is multiplying by the reciprocal. Since this has no index dependency, we can bring it outside the summation. Cool, we like that. Clearly, pi squared, h bar squared, a squared, they're all squares, so we can put it inside this parentheses. And in doing so, we see that the factor of a cancels. Who would have thought energies don't really need the length of the well here in the second order, because we're just looking at what makes the orders change in the power series. So that's kind of cool to see. However, we're stuck with this summation here. So let's recap everything together now. All right. So we saw that we could technically end the problem here, and we just have to sum over all the states in an M. However, that's not exactly suffice for what we can do, knowing that we have the condition that M cannot equal N, otherwise we divide by 0, and we need odd numbers. And actually, this reciprocal here can be found explicitly thanks to the comment in the statement. So if we go and try to find that, then we see we have to use some clever algebra in order to simplify this down. So first, we have to use the multiplicative identity, which is multiplying by 1. Oh, excuse me. And in this case, 1 takes the form of negative 2n over negative 2n, because we can manufacture what the 1 looks like. Okay. And we see that we get a negative 2n up top, the 2n can in the denominator can come out front, and we take this negative and apply it to this parentheses, hence the negative n plus m there. Alright, so flipping that order, we get m minus n there, we put a box around and bracket this up, because now we're going to use the additive identity, or adding 0. And the 0 that we choose is plus m and minus m. And after these two steps, additive or the multiplicative and additive identities, we can quickly see that we get a nice set of parentheses here, m minus n minus m plus n. Okay, so factor that out for the n's, we're good to go there. From here, we're good to go in breaking up this fraction here. So let's go ahead and split up into parts, and we see that we get some cancellations. That's pretty nice. We get rid of them pretty quickly. And so what we can deduce from this is that the 1 over n squared minus m squared comes in the form of 1 over 2n times 1 over m plus n minus 1 over m minus n. That'll be pretty cool. But the actual insight here is what's going to happen next when we take a trial case. So let's try that. All right. So for this particular attempt, we're going to let n equal 1. And pay attention to the blue. Okay, n equal 1. If we plug in n equal 1 here, we get 2 times 1. That's just the form. M plus 1 and m minus 1. Again, noting here that m cannot equal n, so n can't be 1. And thus the rest of the numbers have to be 3, 5, 7, and so on. Okay, so from that, we now have two fractions that we need to color code. So we have a green and a purple with a plus and a minus. Now, because of this nice little minus sign in between, we get something nice coming out. So when we start summing over a few terms, we get 3, 3, 5, 5, 7, 7. And now we see we need to reduce this. This goes to 1/4, 1/2, 1/6, 1/4, 1/8, 1/6. But that minus sign from the reduced fraction, we see that this 1/4 cancels with this 1/4. We see that this green 1/6 cancels with that negative 1/6. And in fact, all these green terms cancel with some successive purple term that can be calculated here. But we have one term remaining, which is the negative 1/2. So we see that we get this is equal to 1/2 times negative 1/2. Cool. Let's go back a little bit to what we originally stated. This was equal to 1 times, or 1 over 2 times n, which n equal 1. But this is also in the form of 1 over 2 times n with n equal 1. So if we put an n there, we see that we get the generalized form of 1 over 2n squared with a minus sign. Okay? And I did this with another attempt, namely with n equal 3 here, and we can see by the summation indices, and we get the same result. 1/6 ends up with times a negative 1/6 from here in the cancellations, so we conclude that this works, again, a little hand wavy from the mathematical perspective, but for all intents and purposes, we have this. So if we plug in this general form for what we have with the summation, we see here that the coefficient out front is 2m times 2 alpha pi h bar after simplification, and we get to incorporate this minus 2n squared. Okay, because that's a square and that's a square, we can put this right into the parentheses. So we have a negative sign that plops out, 2m carries away, and we see that we get a cancel of 2 and 2. And so we get a nice compact expression for the nth state energy. So we can now say what the corrected energy is for the second order, which is negative 2m, 2 over alpha times pi h bar n squared, and that's a pretty fun result. I was not expecting to see something so tidy from a theory that is notably pretty messy. And if you have Mathematica or use Mathematica notebooks or Jupyter notebooks, trying to get enough of these terms out is a lot easier doing something in that computational program than it is just trying to bash your head on the keyboard or table, however you're writing it. So that might be something of value to you as you go through some of these problems. But with that being said, we're now done with stop 1, so let's head to stop 2. Oops, that should be a 2. My bad. But what we see here is that for part B, from problem 7.2, we know that we can use the perturbed Hamiltonian. Remember that all we did in problem 7.2 was take the spring constant and expand it by an amount epsilon. We don't know what it is, otherwise it'd be pretty quick just to plug in the new constant, but now that we have that, we can go ahead and use the perturbed Hamiltonian with the expectation value and be good to go. All right? So again, we have this situation where we have 1/2 epsilon k x squared, but we know that dealing with the harmonic oscillators, nothing is just nice and easy, especially when we're acting on some state m and some state n. So to combat this x squared and find the expectation value, we're going to use equation 2.70, which is the raising and lowering operators, or the ladder operators, the annihilation operators, whatever text you're using, that's what they're called. Same concept though. So by plugging in the x operator in terms of the ladder operators, we get this expression. Now, do note here that we have h bar over 2m omega, and when we square that, that'll come out front. But because this is written in terms of m and omega, we know that that relates to k because k was, or rather that omega was equal to the square root of k over m. So solving k for, or solving that for k, we get omega squared m. And after we square the square root, we get these constants, and we see that they graciously cancel. And that's much nicer because we were told to kind of write this in terms of the classical frequency, at least in 7.2. And so this at least is a lot easier to deal with. The next hard part is coming in. How do we deal with these ladder operators, especially in the square here? So the first step we have to do is distribute. All right, this is going to get a little chunky, so you might want the PDF for this step. But when we distribute, we have plus acting on plus, plus acting on minus, minus on plus, minus, minus. So all possible combinations there. Remember, these are operators, so the order does matter. Don't just distribute them like you would with any other quadratic notation. A plus b squared does not necessarily equal the a squared plus 2ab plus b squared. That's only in real numbers. Doesn't really work here for operators. Nonetheless, we're good to go now. So what we have to do is due to linearity, we can break up this expectation value into 4 independent expectation values, as we see here. Now we have to recall our friends from 2.67 to tell us what happens when I apply the raising operator to the nth state, and what happens when I apply the lowering operator to the nth state. Well, what we see here is that a on n gives us an n plus 1, but we have to advance the state by 1. Lower on n, we have to lower the state by 1, and then we have a square root of n that tags along. Similarly, we add and we minus. Cool. Now applying the successive transformation, or operator rather, we add to the n plus 1 state, which gives us an n plus 2. So we're form matched there, we're good. And now we're trying to raise an n minus 1 state, so that brings us back to n. So if we have n minus 1 plus 1, we just get a square root of n there. Okay, and then again, we see we're trying to lower a n plus 1 state, so we get n, and that leaves us to bring the square root of the current state before application out front, so we're good there. And of course, lower on another state, we get n minus 1. Cool. Now we just have to simplify very carefully. We notice here that within the theory, we started with stationary states, time independent, separation of variables. All those led to a complete set of solutions in the mathematical sense because they're orthogonal, orthonormal, complete, so on and so forth. So instead of writing these as integrals, we can use the Kronecker delta because they are normalized and they are orthogonal, or they're orthonormal. We can write them as the Kronecker delta, and we see that after combining square roots, n times n gives us, or square root of n times square root of n gives us just n. Same thing, n plus 1. Join that square root together, no big deal. But instead of, again, the integrals, we have the Kronecker delta, which will make this simplify so much easier. Here's the first round of simplifications, and in the summation, we're told that m cannot equal n. So because of that, this Kronecker delta goes to 0. This Kronecker delta also goes to 0. That helps us simplify. Now all we're left with are these little mixed indices states where we have m and n plus 2, and then m and n minus 2. Of course, we have our energy hiding down here. Of course, we'll factor that h bar out, and then we'll also bring this outside the summation, so it should calm down and cancel out pretty nice. Let's see how we can finagle this. All right, so we bring the epsilon h bar omega over 4 out, but again, remember we're squared because we had the magnitude squared in there. Okay, we factored out an h bar omega from both the energy terms, and voila, that 1/2 and 1/2 cancel. How beautiful is that? We don't need the cross terms anymore because the Kronecker delta versus the summation indices, they're not going to match, so we're good there. So bringing this h bar omega out front, we cancel that with one factor of the square here, so we're good to go on that front. Now, here is the tricky part. Whenever we square this thing, we have to be really careful, and I really advise you to look at the PDF for this little sketch proof of why it is. You see that whenever we square this out and distribute, we end up with cross terms again, and due to the restrictions on the indices for the summation and how the Kronecker deltas add up, we see that if I'm joining together delta of m where the other side is n plus 2, they have to be equal. And if I also have to be equal to m equal n minus 2, right, then by the cross terms that you get there, setting those two conditions together lead to more Kronecker deltas canceling by definition. Again, a little hand wavy for everything, and we can just kind of see how they finagle with the plus 2 and minus 2 canceling, leading you back to the Kronecker delta of m and n, which can't happen inside this summation, so those cross terms go to 0 yet again. So we're wonderful, we like that. And also note that Kronecker delta means that you're equal to 1, so squaring 1 would just lead you to 1, squaring 0 would lead you to 0, so we just get the Kronecker delta back. It's a lot easier just to see the PDF for that little sketch proof, but with that, we're good to go to facilitate how to deal with this summation now. And as you see, much like we did in part A, we're now going to split these two up. So from that splitting up, let's go ahead and see what this Kronecker delta does in terms of our state M here. So when we plug in, again, the only restriction on the summation was that M cannot equal N. Cool. The Kronecker delta tells us that the only states that matter if we want something to exist is for the state of M equal N plus 2, which we see in green, and M equal N minus 2, which we also see in green. Okay? So it really doesn't matter what those other terms are because the Kronecker delta makes our life easy. So that's why we don't have a summation anymore. That being said, whenever we plug in the states, the requirement of the Kronecker delta into this and distribute the negative, we get the n's canceling in the denominators. Beautiful. That leaves us with a minus 2 here and a 2 here. So since both of these fractions have a minus 2, or excuse me, since both of these fractions have a factor of 1/2 in them, we factor that out. That's what the 2 is doing there. But this negative needs to be distributed to this polynomial, which is distributed from the n plus 1 times n plus 2. Similarly here, distribute that in, you get n squared minus n. But the negative here gets enforced onto this fraction, which is why you see the green negative signs on this set of polynomials, or this set of factors rather. And then of course we're adding the n squared minus n. So once again, cancel, the n squares cancel. Beautiful, beautiful, beautiful. And then we have a minus 3n and a negative n. That gives us the negative 4n. 16 times 2 gives us 32. We're left with the negative 2 by itself. Wonderful. Again, to try to help simplify this down, we see that 32 is equal to 4 times 8, which is represented here. We factor out the negative side from the bracket, so we're good there. And instead of having 2 here, we just multiply by 4 over 4. That way we can factor out a factor of 4. So we get n by itself with a 2 over 4, which just reduces down to 1/2, so we can kind of keep up with the original ground state energies. Okay, so 4 cancel with 4, and we're left with the second order energy corrections of E2n equal negative epsilon squared h bar omega over 8 times n plus 1/2. Beautiful. Of course, let's rewrite this to make it a little more easy to put in terms of the ground state energy, which this should be E0, not necessarily En, but nonetheless, we see that we can write this in terms of the original energies. So we're really cool there, and that is really awesome. But one thing we should note here is that in finding this second order correction, that negative 1/8 epsilon squared is the second term from part B, or excuse me, from the exact solution in 7.2. That is freaking cool. So that exact solution is telling us that perturbations for the harmonic oscillator namely come with the spring constant K or the omega. That is really awesome. Very, very cool. Alright, so enough of my rambling. I think you saw how cool that was. A lot of different algebraic steps and manipulation as always. Quantum theory will never leave you bored when it comes to math, and this is still baby quantum theory. The higher level stuff, whenever you deal with Lagrangians and field mechanics, that'll be really fun to see come to fruition. That being said, you see how important things like the infinite square well, or also known as particle in a box, is, and more importantly, how rapid and important that harmonic oscillator is to all of physics. It cannot be understated how many times you're going to see the harmonic oscillator. It will come back again and again and again. So, that being said, I need to give a massive thank you to all my supporters for making this possible. I'm extremely grateful for your support. If you'd like to see more, you can also become a patron for access to supplemental material, current and future projects, and one-on-one help. New content is posted weekly to fuel your curiosity. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. Though I can, I think I do a good job of explaining it, so does everybody else. What is a good job? Well, that's up to you. You have to be able to see things from several different perspectives, and I might not say it the way that best suits you, so definitely check out other options that you see available, and then try to formulate the theory in your own mind with your own words, and then try to explain it to somebody else. That's how you're best gonna come to understanding these topics, especially when there's so many moving parts. As always, thank you for watching, and until next time, stay curious.